Assalamu alaikum, Chem 30. So what we're going to do is retrace or sort of review acid-base titration. A lot of this is going to be similar to what we did in Chem 20, but in Chem 30, now that we have the context of buffers, what buffers are going to do is they're going to explain why certain curves are flat and other ones are not, and why some types of titration have more than one flat region. So just like it was in Chem 20 and in redox titration, the purpose of titration is to, it's kind of twofold. So the first and probably the most used one is to find the concentration right? So find the concentration of an unknown. And so we usually use a known concentration to help us see how long it takes to neutralize the unknown concentration, and with that we can work backwards and find the concentration. And then the second purpose is to safely and effectively neutralize or complete an acid-base reaction. And the reason why it actually allows a full neutralization to occur is because, and we'll write this in purple here, the slow and constant drip rate, so we'll say drip rate, allows acids / bases to fully react with every drop. Okay? And so if you allow it enough time, and they can fully react, what we do is we create, here's a keyword from the beginning of the unit, quantitative reactions. So quantitative reactions, which means that it has a single arrow, even if it's a weak acid and a weak base, or a weak acid and a strong base. And then lastly, titrations and their curves, rely heavily on buffers and buffer regions. So we'll write buffers here and buffer regions, and those are going to be the flat lines of the graph, and you'll see that when we do some titration curves. So when we go and draw titration curves, there's two things that we can sort of rely on. First, they depend on the type of acid-base titration that we're doing. And by that, we're talking about if it's a strong acid, strong base, weak acid, strong base, and of course a polyprotic titration. And they're also dependent on what the titrant is. And remember, the titrant is the substance in the burette so the substance in the burette, and it's added to the sample. And remember that the sample is the substance inside the Erlenmeyer flask, or inside Erlenmeyer flask. The other factor that influences the titration curves are the types of titrants and the samples that are inside the burette and in the Erlenmeyer flask, and in particular, what kind of acids and bases we have titrating against one another. So the first category that we're going to look at, which is something you would have seen in Chem 20 most likely, is a strong acid versus a strong base titration. So let's say our strong acid, which would be any of the first 6 in the data booklet, would be the titrant, which is the substance inside the burette, and had a strong base, meaning anything with a hydroxide ion directly attached to it, would be the sample. Now, this pH diagram is going to represent the pH changes that the sample goes through, not the titrant. And so if the sample is a strong base, it's going to commence at a pH that is far greater than 7. So start at a high pH. As the titrant of the strong acid is added to it, it eventually goes down at one point very sharply and then becomes an acidic solution towards the end. The point where the H3O plus and the OH concentrations equal each other is called the equivalence point. And for strong acid and strong base titrations, it's always going to be at 7. So the midpoint over here, when we extrapolate it, it should always be at a pH of about 7. And in fact, anything with an equivalence point of 7 is an indication that we have a strong acid versus strong base. Now, what we didn't cover in Chem 20, because this is essentially the same thing as we covered in Chem 20, what we didn't cover in Chem 20 is why these relatively flat regions on the pH curve arise from. And essentially, these flat curves or flat portions of the curves or the flattening curves are from what we call buffer systems, which we briefly discussed last class. And remember that a buffer system is a weak acid and conjugate base somewhere inside the acid-base system, which is going to work to resist pH changes. Hence, leaving very little change in pH at each end over here. But in order for it to be a buffer system, it has to be a weak acid with its conjugate base. Now, let's say this is indeed a strong acid and strong base titration. An example of that would be HCl plus NaOH. Now, the thing is, we need the net Bronsted reaction, right? The whole spontaneity thing that we were doing to predict acid-base equilibrium, we need to write that out. And so, to do this, if this is a strong acid, it's going to split into H plus and Cl minus, and all bases are going to split into their cations and the hydroxide ions. And since this is aqueous, we're going to list water as well. So we're going to go H plus, Cl minus, Na plus, OH minus, and of course H2O. We would label all the acids and bases and cross out any spectator ions, and then we would identify the strongest acid with the strongest base and react those two together. Writing the Bronsted reaction would look like this. H3O plus OH minus yields to 2 waters, H2O plus H2O, or we can simplify it and combine the two and just write 2 moles of water on the product side here. And if you look at it, even though this is a weak acid and strong base reaction over here, we wrote a single arrow. And that's because if you remember at the beginning of the video, when we drop things at a constant rate, we allow these two entities to fully react with each other, hence creating a quantitative reaction. Now, we have a weak acid and its conjugate base. Over here, the H3O plus is officially considered a weak acid, and here's its conjugate base, and this here is a buffer system. This buffer system is officially responsible for the flat curve over here. So at this region, we have H3O plus OH minus, which yields to H2O. And so the buffer, 2H2O more specifically, the buffer system here is what causes that flattened or relatively constant pH until at this point the buffer system is overcome. At this point, we no longer have OH minus present because it has now been converted into H2O. But the thing is, if the acid is in the titrant, we keep adding the acid to the H2O. And so what ends up happening is you have this reaction. H3O plus H2O, and remember that H3O plus came from the ionization of the strong acid. And that's going to yield to H3O plus, as this donates a hydrogen to the water, plus H2O all over again. And this is going to be the final acidic solution. Now, why would that cause a flattening? Well, again, if you look at the system, we have a weak acid present over here, and its conjugate base present over here, the water molecule. It's quantitative because the reaction happens at a constant rate, which allows both of the ions to fully react with each other. And hence, we have in this entire strong acid, strong base titration, we have two buffer systems. The first one occurs at the top, which is going to be the H3O plus to H2O buffer system. And the second one is again the same buffer system repeated of H3O plus and H2O. And hence we have two flat regions of a strong acid, strong base titration. Now, one thing I want everybody to understand here is that this is going to be constant. So whenever you have a strong acid versus strong base titration, you will always have an equivalence point of 7 and two buffer systems. Now, let's say the roles were reversed and the acid is the sample and the base is the titrant. Everything else would be the same except the graph would look reversed and the curve would look inverted here. We would start at a low pH and we'd end up at a relatively high pH. However, the equivalence point right over here would still be at 7. Okay, so we write equiv point. And you would still have the same buffer regions of H3O plus and H2O and H3O plus and H2O that are present on both ends of the graph. The only difference is, and again this is the same thing that's repeated for the acid as a titrant and the base as a sample, this reaction comes from H3O plus OH minus, and this one is from H3O plus and H2O. But all of these properties here, whether the titrant and the sample are switched, is still going to be repeated. So whenever you have a strong acid versus strong base in any way, shape, or form, you're going to have an equivalence point of 7 and two buffer systems present. The second likely type of titration that you're going to encounter is a weak acid versus a strong base. And again, it doesn't matter whether the acid is the titrant or the sample, the curves would just be switched, but the number of buffer systems and the equivalence point is going to be the same. So let's say in this case it's the sample, which means that it's going to start off at a pH below 7. So let's say it originates over here. I see the middle of the graph is 7. And so anything below 7 would be, an acidic pH. So let's say instead of starting at 1 down here like the strong acid started as, we'll start at around like a 3 or a 4. So it's going to go like this for a certain amount of time, and then once the buffer system is overcome, then it's going to rise up. And remember that a strong base, again, refers to anything that has a hydroxide ion attached to it. Now, the equivalence point, or where the H3O plus and the OH concentrations are equal, is going to occur in the middle of the graph. But one thing you'll notice that's different than when we compare it with the strong acid and strong base titration is that if that's the 7 mark, this one is above 7. So we're going to write here, and this is always going to be the case for a weak acid and a strong base titration. Now, the equivalence point is above 7. Now remember, when we're talking about weak acids, we're talking about anything that is not within the first 6 acids. So let's say we write a reaction between a weak acid and a strong base. I will say that the weak acid is hydrofluoric acid plus sodium hydroxide. Now, just like we did previously, we have to write the net Bronsted reaction between these two entities. Now, because this is a weak acid, we're going to list hydrofluoric acid as is. We're going to split up the base, since it is an ionic compound. And because these are solutions, we're going to add water in it. We're going to label all the acids and bases and cross out any spectator ions. And we're going to identify which one's the strongest base, which would be the OH ions, and of course the strongest acid, which is HF. Next, we combine the strong acid and the strong base together and write this Bronsted-Lowry reaction, whereby we check and see are there any buffer systems present. Now here's your weak acid, and its conjugate base, the fluoride ion, is on the other side. So here's the conjugate base. And so this over here is the first buffer system. And it's a legitimate buffer system. And this buffer system, the HF to F bitus, is what's fully responsible for this buffer region over here. So here's the buffer number 1. And so the reaction listed under here is HF plus OH bitus gives you F bitus plus H2O. Now the short form for this reaction, for the cause of that flattened pH curve, would be HF and F bitus. That's the buffer system. Here's the thing. HF no longer exists. At that point, all we have is F minus into the solution. But the base, or the titrate, is the base over here. So at the top, you'd have F bitus plus OH bitus. Now that's just a base and a base. And I'm going to erase this part so we have a bit more room to write. But a base plus a base is not spontaneous or not reactive. So we're going to write no reaction at the top. And so the only reason why here that the pH remains constant is because there is no actual reaction at this point. So actually, weak acids and strong base systems only have one buffer system. And so they only have one buffer region. And again, why? Because at the top of the titration here, the only reason why the pH is not changing is because they don't react with each other. A base and a base will not react. So really, the only buffer system that is truly present here is HF to HF bitus. And so the main takeaways for this titration type is that for a weak acid versus strong base, and it doesn't matter which one is the titrate, which one is the sample, your equivalence point is greater than 7, and they only have one buffer region, because on the second flat curve, it's just a non-spontaneous reaction. Last but not least are the polyprotic titrations, and these ones involve a significant amount of work. Now, for these to take into effect, only one of the substances has to be polyprotic, which means if it's a base, it'll accept more than one H+, and if it's an acid, it'll give away more than one H+. And so a good example here would be H2CO3 plus KOH. And we know that the net reaction would remove the K+, and you would basically just have H2CO3 plus OH minus. Now let's say that this here is the sample. This is how the graph would look. You would have two buffer regions at two equivalence points, but let's prove each of the buffer regions. So you got two equivalence points here, as there appears to be two steps. So this is equivalence point 1. And here's another equivalence point. But that's not going to be the focus of this exercise. We just want to show you where that would be. What we're going to do is conserve our space here and write full reactions. And sorry, we said that this is the sample. Actually, we've made it the titrate. So we're going to say that the base is the titrate, and your H2CO3 is the sample here. So the first reaction between H2CO3 and OH minus, which is basically dropping on top of H2CO3 from the burette, it would be like this. I'm going to write it in purple so that we can see. Now, the first buffer system is relatively easy to spot. You got a weak acid here, and its conjugate base is over here. So here is the first buffer, which again causes that first flat curve. So we're going to go to the bottom here and write buffer region 1, and that's produced by the H2CO3 and HCO3 minus buffer system. Now over here, remember that now the H2CO3 has been eradicated by the OH minus. What we have instead is the hydrogen carbonate ion. Now while this is the new entity present, we still have OH minus from the burette dropping on top of HCO3 minus. So we're going to write HCO3 minus plus OH minus. And that's going to yield to, in this case, this is the stronger base. So it's going to remove the hydrogen here, and it'll be CO3 2 minus plus H2O. Again, the buffer system here is going to be present, and it's HCO3 to CO3 2 minus. So at this region over here, we will have a second buffer region, and the buffer system, or buffer number 2, is going to be HCO3 minus to CO3 2 minus. This is the weak acid, and there's its conjugate base. And this is going to cause the resistance in pH at our second step over here. Now, much like in previous questions, we now no longer have any acidic properties left, or acidic substances in our products. CO3 2 minus is a base. So at the top here you'd have CO3 2 minus, but we still have hydroxide from the burette that is pouring down. The problem is that both of these are bases. And so here, you would actually have no reaction. And so on the flat region number 2, so flat region 3 we could say, this is not a buffer because the only reason why the pH stays relatively constant is because there's no reaction over here. So we're going not a buffer, it's just a base plus base. So in total, this polyprotic titration, in which the polyprotic substance is over here, it's a polyprotic acid, right? It could give away 2 H's, has 2 buffer regions, and 2 equivalence points. Now what I want you to do is, I want you to pause this video and try this one on your own. Phosphoric acid, or H3PO4, as the sample, so I should see this graph starting at a lower pH, is titrated with hydroxide ions as the titrate. Pause this video and try this out yourself and see if you can identify the number of buffer regions as well as the number of equivalence points. And I want you to identify what the buffer systems are at each buffer region. Okay, hopefully once you tried it out, these are the reactions that you got at each step here. We have phosphoric acid initially react with OH minus, creating this buffer system. So here's the first buffer, which is H3PO4 to H2PO4 minus. And then since that's eradicated, but hydroxide still keeps reacting with the new substance, our next staircase, this here, so the first one was here, this is the next one over here. We have H2PO4 minus making a buffer system with HPO4 2 minus. And then after this reaction, this is eradicated. Our H2PO4, we got HPO4 2 minus, which carries on over here, and I'll write it a different color. We'll do this one in yellow. And then in this region over here, we got HPO4 2 minus, making another buffer with PO4 3 minus, and that creates the flat region that we see over here. So we have 1, 2, 3 buffer systems. Of course, at this point, PO4 3 minus plus hydroxide would just be 2 bases added together, and so they would just yield no reaction. And so when we label all the buffer regions, the first buffer system is created by the H3PO4 to H2PO4 minus. The second buffer system is created by the H2PO4 minus to HPO4 2 minus. And the third buffer system is created by the HPO4 2 minus to PO4 3 minus. And of course, the final flat line is just because PO4 3 minus plus OH minus creates, well, it's no reaction, so the pH is not going to change. The last thing that we're going to mention briefly here, and this is repeated from Chem 20, is that it's important to use the right indicators for a titration, because if you don't use the proper indicator, then what happens is you'll never know when you reach the end point or the equivalence point, because it won't turn colors at the right time. So it really depends on what kind of titration you have. For strong acid versus strong base titrations, remember that the equivalence point, okay, is always 7. And so you need to choose an indicator that has 7 inside its pH range. So if we're thinking about some indicators that have 7 inside its pH range, whenever it comes to a strong acid or strong base titration, some good indicators to use would be bromothymol blue, phenol red. As well, Cresol red has 7 right inside its range. So I guess we could also write Cresol red. And again, the idea is to choose an indicator that has its equivalence point at its proper range. Now here, when it comes to a weak acid versus a strong base, remember that the equivalence point is greater than 7. And so we want to get indicators, depending on what the exact equivalence point is, it's got to have a pH range that is greater than 7. So usually phenolphthalein are good indicators. So if I got a equivalence point of, let's say, about 9.0, like a pH value of 9.0, then phenolphthalein is good because it's inside that range. Sometimes as well, depending on how much above 7 it is, phenol red could be 1 because it goes all the way up to 8. And again, it just depends on what the exact equivalence point would be. So in short, just like in Chem 20, you look at the equivalence point based on the type of titration that you have, and you choose the indicator that has the equivalence point inside its pH range.